The energy field,
Electric field,
or electric field, sorry.
electric field will change. Well, which electric field are you talking about?
Of the plates.
No, that will change.
It will, okay.
A big thing when you're dealing with these problems is that if it's still connected to the same power supply, then my voltage is not going to change. So my voltage is still 20 volts. My total electric field well, it's still my voltage divided by the distance between them, so that's 20 over 0.05. So my total electric field is 400 newtons per coulomb, or coulombs per meter. That also stays the same. However, my capacitance does change. Because my capacitance, if I have a dielectric in there, kappa epsilon sub naught A over D. Or even without a dielectric, the kappa is equal to 1, but epsilon sub naught hasn't changed, A hasn't changed, the distance between the plates hasn't changed. The only thing that's changed is that this value of kappa, so my capacitance is just twice what it was before. 3.54 times 10 to the negative 10 farads.
How do you know how K? Oh, sorry, I missed where you defined.
Yeah, I gave you kappa for this dielectric. Now I can find the charge. How do I find the charge on the plates?
So there's this charge density times area.
Except I don't know the charge density.
You could do, C times the voltage.
Yep. Going back to the definition of capacitance, which is the charge over the voltage. So, 20 times this. 7.08 times 10 to the negative 9 coulombs.
Yeah.
And so now I can find the electric field because of the plates. Which is just surface charge density divided by epsilon sub naught. This is sigma over epsilon sub naught. And that's Q over A divided by epsilon sub naught. So 7.08 times 10 to the negative 9. My area is still 1 square meter divided by 8.85 times 10 to the negative 12. Well, area stays the same. Epsilon not is the same. If I double my charge, I should be doubling that electric field, so that should be 800. Did you do that math?
I'm still working on it, sorry.
Okay.
Yeah, that's what I got.
Okay. So by putting the dielectric in there, we suddenly increase the amount of charge that we're holding onto the plates, that we're putting on the plates. So if I picture my plate here and here, I have 800 newtons per coulomb going that to the right because of the plates, I know that the total is 400 newtons per coulomb, which means my dielectric, the electric field from the dielectric must be 400 going that way. Because I have two 400s here, let's just be a little bit more explicit. This 400 is the total electric field. Total. This is the electric field because of the plates. And this is the electric field because of the dielectric. Which is just the difference between those. Questions to hear?
How do the plates have more energy than the total?
How does it have more? Because the total electric field is the sum of all the electric fields. So I've got two competing ones. I've got the plates with the charge on it, then I have all these little dipoles in the dielectric. So this increases, so the total still stays the same, but this has to increase in order to offset what the dielectric is doing.
Is that, okay, because it's going in different directions.
Right.
Okay, okay, thank you.
So if the total would have been 500, this would have been 300.
Thank you.
Thanks for that explanation. Why does the total electric field stay the same?
The total electric field, conceptually, we're putting more charge onto the plates. If that did not happen, there's no point in putting a dielectric in there, except maybe to get the plates closer. But the dielectric allows you to store more charge on the plates. So we're getting more charge on the plates. And because there's more charge, the electric field from the plates is increasing, and it offsets the electric field going in the opposite direction by the dielectric. I think I veered off your question at some point. What was it again?
No, I think that answers it. Because, even though it just offsets each other, it stays the same.
Yes. All right. Other questions before we change this capacitor?
Why are we changing the capacitor?
Because suddenly new specs have come down to you. All right, so we've got for the plates, total, all right, so we've got that information there. So now what we're gonna do, we're gonna disconnect the battery. That eraser will not work on this. So we now disconnect the battery. And we do it so beautifully, we do it so quick that we don't lose any charge. Now, in reality, if I disconnected the power supply from that, it's gonna spark a little bit, and I'm gonna basically lose the charge on my plates. So, because this is a nice board problem, I can disconnect without any loss of charge. But physically, I cannot disconnect fast enough in order to really maintain what I'm telling you. Disconnect battery, ideally.
I'm so sorry, would you mind moving the camera?
You just want to see everything, don't you?
So this is technically like the state, like when you're like like a nanosecond, like after you disconnect the battery, assuming you do it like theoretically incredibly fast.
It would have to be on the order of microseconds as slow as
Okay.
to disconnect. Yeah, my reflexes. Maybe when I was younger.
Is it physically possible, or is it more just theoretically possible?
It is, there are contraptions out there where you can do that, just by hand, no. I don't think anything's fast enough for that. Okay, so we've now disconnected the battery. What's the voltage? What's the total electric field? What is the electric field from the plates? What's the charge? And the capacitance. What changes because I've now disconnected the battery?
See the voltage,
How did the voltage change?
go to 0.
Well, we still have, it actually will not go to 0. There's still a voltage there. There's still a potential difference. If I have an electric field pointing in some direction, I've got a potential difference.
Does the charge change?
Where did the charge go?
Just distribute through the wire, I guess.
It's already distributed through the wire. And also, any charge, if you lose an electron into the wire, you're not gonna lose any significant number.
So since it was ideally disconnected, does that mean that the charge is the same?
Yep, charge is the same, so that's 7.08 nanocoulombs. If the charge is the same, what else therefore has to be the same?
The capacitance?
All right, why does the capacitance have to be the same?
Well, because charge equals volts times capacitance.
And you're saying the voltage is the same?
Oh no, voltage changes, so capacitance also has to change.
Okay. Also, look at it from this point of view. When we disconnected it, what changed here?
Kappa.
No, the dielectric is still in there.
The electric field of the plate stay the same?
They will, because the charge is the same, electric field from the plates will stay the same.
Yep.
So that was 800 newtons per coulomb.
Because it's just charge over area divided by epsilon so naught.
Yep.
Will E total, will the electric field total stay the same?
Yeah, because the electric field from the plates is still causing the dielectric to polarize the same way. So this is still 400 newtons per coulomb.
And so the dielectric also has to stay the same?
Yeah, disconnecting the battery doesn't affect the dielectric.
So that's also the same?
Which
Or-
one?
Or did we not have to? I was saying, electric field with dielectrics also.
Oh, yes, that would still be the same. I didn't have that on this list, but we can squeeze that in here. The electric field, absolute value of the electric field from the dielectric is still the difference between these two. Think about the ED equation. The total electric field and the distance stay the same, so what does that tell you about the voltage?
The same?
The same?
Yep.
Everything's the same.
Yep, everything, nothing changes. Because in this equation, right, for the parallel plate capacitor formula, the kappa epsilon naught A over D, none of that changes just by disconnecting the battery, so capacitance is still 0.354 nanofarads. So none of that was particularly exciting, it's just the same, disconnecting the battery doesn't change any of it in our nice, again, ideal situation. So it'd be really incredibly boring if I just stopped it right there, so it's not. And now, I'm going to separate the plates. Separate plates to, let's just double it. Twice the original distance. So they're now 10 centimeters apart.
Is it still disconnected?
It's still disconnected. So what's gonna stay the same?
The voltage,
It will not.
really.
Thing.
Hmm.
Separate plates.
Think about physically what's going on here. I got the two plates with charges on it a certain distance apart. I disconnected the battery and now separate them. What cannot go away?
Charge?
Charge. Charge stays the same. It's still 7.08 nanocoulombs. This is an important thing on these problems here. If the battery is still connected, voltage will stay the same. If you disconnect the battery, charge stays the same.
This is a little bit off topic. When, for the tests and stuff, are you gonna give us the SI prefixes on there?
I've done it in the past. I don't know if I automatically do it or something I just write on the board.
Okay. Cause I don't remember those outside of a few,
I think you're just hanging around with the wrong kind of people.
probably.
Yeah, usually me and my friends, we talk about that stuff all the time.
Darn straight. All right, so charge stays the same. Now let's take a look at the other things. Capacitance. All I've done is I separate the plates by two more, and I do need to throw in one other bit. And dielectric magically expands to fill it. So say dielectric just fills up the entire space again.
Oh, because if there's a space in the dielectric, you'd have to count for the free space in between as well.
Yeah. Which I don't want to do right now. Wait.
So does that mean the,
So, what was that little notation you wrote about the dielectric?
The dielectric magically expands to fill the space.
so that means that the electric field of the plates stays the same?
Because the charge stays the same, kappa still staying the same throughout, yes, the electric field from the plates stays the same.
So the total's also the same?
Yep, that would stay the same.
And so the dielectric also has to stay the same?
Yeah, because the dielectric is staying the same. Because for the total, I've got two formulas for it. I got the ED formula, and I also have sigma over kappa epsilon sub naught. Yeah, sigma over kappa epsilon sub naught.
So the electric field will stay the same even if you change the distance of the plates?
Okay, so one of the reasons why I just doubled the distance, I have 1 meter by 1 meter plates. So 10 centimeters apart puts me at 10% of each of those dimensions. So I'm still within the infinite plate approximation. If I tripled it with keeping it 1 meter by 1 meter, suddenly we're into that gray zone of, can you assume that they're parallel plates, infinite parallel plates anymore? So in reality, it would change if I change the distance between the plates. But as long as that distance is 10% or less of one of the dimensions of the plate, then it's okay to assume infinite plates. And the sigma over epsilon, or sigma over epsilon naught approximations.
Because of the voltage over distance thing, wouldn't the voltage go to 40?
ED, so we doubled the distance, so yeah, that's 40 volts now. And what would happen to the capacitance? That's not equal, but goes to.
It would, be halved.
Yeah. So making the plates farther apart gives you a smaller capacitor. Smaller in the sense of less capacitance. And there you go. You can pretty much be sure that on the second test, there's gonna be a problem like this. I give you a certain setup, and then just start manipulating it. Or, there's one test where I gave you the setup and I said, I want you to double the voltage, but keep these other things the same. And the first time I did that, I made a mistake, and one of them was impossible. Second time I did it, I said, if it's impossible, please show why.
So this is material that will be on test 1B?
Yes.
And test 1A is Monday?
Yes, the 30th. If that's Monday.
So what is that, does that just go to Gauss's law?
Then the chapter after that goes through chapter 27.
Okay.
No. 3, 4, 5, and 6, through 26. First 4 chapters. Questions?
So everything from chapter 23 to 27?
23 to 26
Oh, okay.
is on 1A,
Not 27.
not 27.
What is this?
This is 27.
So, okay, this one.
I could throw this onto the first test.
I mean,
I've done it before.
We gotta do all that.
In a previous textbook, the basics of capacitors was thrown into the same chapter